So in our last video, we talked about Bohr's model of the atom, and Bohr imagined electrons rotating around the nucleus in these perfectly circular pathways, and the electron followed the same pathway every time it went around the nucleus, just like a planet around the sun. And he decided this by studying the light emitted when electrons entered the excited state and then fell back down to the ground state. So the predictions that he made for hydrogen when its electron got excited and then fell back down were correct. But the problem with Bohr's equations were that they only worked for hydrogen that has one electron. So de Broglie came along and he kind of said the opposite of what we've been talking about. So we've been talking about light, which we formerly thought was a wave. And we thought that now light can sometimes act like a particle. And now de Broglie is saying the opposite. He's saying that there are some particles in matter that are so small that some of those particles actually have wave-like properties. And an electron is an example of one of them. They're so small and they're so fast that they don't always behave just like particles. Sometimes they behave like waves too. Okay, so that is something that's important. So what he did was he combined these two equations that we've looked at already. So if mc squared and hc over wavelength are both equal to energy, then we can actually set those two equations equal to each other. Okay. And most of the time with this equation, you can really manipulate this to solve for anything, but most of the time the question wants us to solve for wavelength. So if I just rearrange this formula, I get wavelength equals h over mc. Okay, and now we're solving for the wavelength of a particle, which originally we didn't think particles had wavelengths because they were particles and not waves. We know that h is Planck's constant, so that's something we have to memorize. C, so previously we talked about c being the speed of light, and I told you to memorize 3 times 10 to the 8th meters per second. So now, because the questions are going to be about particles and not light, the speed is going to be different. So either they're going to give you a speed in meters per second, or you're going to have to maybe solve for the speed of the particle. M is mass, and the mass has to be in kilograms. Sorry guys, kilograms. And the reason why, if we look at the unit joule, which is the unit for energy, that's kilograms times meters per second squared. So in this equation, when we're making sure that all of our units are canceling out, the mass has to be in kilograms. So that's another conversion you might have to make. Okay, so let's look at an example problem. So like I said, they're asking us here to solve for wavelength. They're telling me that it's an electron, so it's a particle that's behaving like a wave. They want me to solve for a wavelength in nanometers. Okay, I can check that out at the end. Okay, and here's my speed. My speed is that. My mass is this. So of course they're giving me the mass in grams, and I know that the conversion factor is that there's 10 to the negative 3 kilograms in 1 gram. So if you guys pause right now and take your calculator and do that number times 10 to the negative 3, everybody try it out. You should get 9.11 times 10 to the negative 31 kilograms. Okay, so now that I have everything in the right unit, I can go ahead and start plugging stuff in. So Planck's constant is 6.626 times 10 to the negative 34 joules per second. And I'm going to divide that by mass is 9.11 times 10 to the negative 31 kilograms. And speed is 3.25 times 10 to the 5th meters per second. Okay. So if you want to multiply the bottom two numbers first, actually, I think this works out if you just do 6.626 times 10 to the negative 34 divided by that mass, and then you can divide it by the speed second. Just make sure when you put these numbers in your calculator that the scientific notation numbers stay in parentheses so that your calculator doesn't do PEMDAS in a different order than you want it. So pause the video, check to see what you get for that. And now that you're back, we should have gotten 2.24 times 10 to the negative 9. Now, guys, if you look at the units for speed, I have meters per second. So what unit in that set of units is for length? Meters. So whenever you're solving for wavelength, you're going to get an answer in meters. And if you want to convert to nanometers, I have 1 nanometer is 10 to the negative 9 meters. Okay, and if I put that in my calculator, so I'm doing my answer divided by 10 to the negative 9, and I get 2.24 nanometers as the wavelength for that electron moving. Okay, so we're going back again to some conversions from Unit 1, and we need to know those conversions to answer this question correctly. Okay, so to talk about why this is all important, so if electrons have wave properties, so in electron microscopes, instead of using light to illuminate objects and see really small things, we use beams that come from electrons, and they have a much higher frequency, shorter wavelength, and we're able to see images that are a lot smaller. So that's pretty cool than a regular microscope. The other reason why it's important is because this idea changed the way we view the atom. So now we're thinking, and this was the work of a lot of scientists together, that instead of the electrons orbiting in those perfectly circular paths and following the same path every time, that the place that the electrons are found in are more like clouds, and we call them orbitals. And orbitals is a really important word for you to know. So it's important to note here that no perfectly circular rings were thought to be the case anymore. So here is we're going to get to play with this animation eventually, but here's a diagram of the atom beryllium, and you'll notice that there's 2 electrons in that first ring around the nucleus and 2 electrons in the second. Okay, and we're assuming that they follow this pathway every time they go around the nucleus. If I choose the cloud model, which is what we really know to be the case now, okay, see that blue fuzzy area? So we still believe that electrons are certain distances away from the nucleus depending on how much energy they have, but where they exactly are is more of a like general region. Like there's a certain probability of finding an electron in this general fuzzy area, not in those same perfectly circular paths every time. So it's a little more fuzzy than we thought. Okay, so this is the wave mechanical model of the atom, and this is what we currently believe the atom looks like. We're going to label this again as like a cloud or orbital. And you'll see towards the end of this unit, guys, we're still going to draw atoms like Bohr drew them for simplicity's sake, but we really know that this is to be true. So another way of saying the word orbital is a wave function. So I just don't want you guys to get confused with like terminology. So when you hear the word wave function, so it's a mathematical equation, and it tells you about the electron's location and its energy state. So it gives you a probability of where you might find an electron. So it's not going to say its exact location, but it'll tell you around where it's going to be, which is another way of saying like a cloud. Okay, so wave function, orbital, cloud, they all can be thought of as the same thing. Okay, and again, we have another definition for orbital, which is a wave function or a probability. So Heisenberg, he came up with the uncertainty principle. And again, this is like restating what we've been talking about. So he's saying that electrons are too small and move too fast to know both where they are, their position, and how fast they're moving at the same time. So you need about 2,000 electrons if you wanted to make something that weighed the same as one tiny proton. That's how small electrons are. So uncertainty, we're never certain about where the electron is and its momentum at the same time. We can figure out one or the other, but never both, because it moves too fast and it's too small. Okay, so now let's talk more about these orbitals. So guys, you're never going to be responsible for drawing these, but you are responsible for knowing what the orbitals are shaped like and how many electrons they all hold. So there are actually 4 kinds of orbitals. I have S, P, and D here, but F is the 4th kind of orbital, and we'll just write that down there. So the S orbital has 1 orbital. And if you had to describe that shape there, we would say it's shaped like a sphere. So that's the general location where we would find an electron if it was in an s orbital. And it holds 2 electrons. So if you know that an atom contains an electron shell that has an s orbital in it, you know you can fit 2 electrons in there. The p orbitals have 3 orbitals. And you can see this in the picture, guys. And if you look at those shapes, these are called dumbbell shapes. Okay, and if we know that 2 electrons can fit in each orbital, and I know that the p orbital has 3 orbitals, then this whole orbital can hold 6 electrons. Okay. Then we have D. So you guys don't have to know the name of this shape. You just have to know that there's 5 of them. Oops. Whoops. I'm looking for my eraser. There it is. Oh my goodness, guys. My page is upside down. There we go. I can't spell anymore either. Okay. 5 orbitals. So we can hold 10 electrons. And the F is 7 orbitals. And it holds 14 electrons. And the F orbitals, if we take a look down here at the periodic table, the F orbitals only fill up in these rows down here. And these elements down here are rarely, I'm going to say they're never talked about. So you really just have to know the F orbitals exist and how many they would be and how many electrons they would hold. Okay. So if we look at this periodic table, now guys, when you take the chemistry regions, the electron configuration is written for you on the periodic table. In honors chemistry, you're responsible for knowing how to write an atom's electron configuration by just looking at where it is on a periodic table. Okay. And basically the electrons fill up in order. So this is the Aufbau principle. Orbitals with the lowest energies are filled up first. So the closer the electron shell is to the nucleus, the less energy it has. And the electrons fill in from the inside out. Okay, so this is a really great visual because it shows you which orbitals fill up and in which order. So you read this from left to right. Then you jump down to the next row. If your element is in the second row, you start filling up the 2s all the way to the 2p. And this is going to make more sense as we do an example. So I'm just going to jump right down to some practice. Okay. So first of all, like to know how many electrons, the atomic number, which is on the periodic table, equals the number of electrons. So before you even start, you should know how many electrons total should be in your electron configuration, and that should help you check your answer to see if it's right. Okay, so for hydrogen, the first thing I want to do is write what period it's in, what row it's in on the periodic table. So hydrogen is that first element there. I'm going to erase this so that you guys can see where I am. You should definitely have your periodic tables out too. Okay, so this right here is hydrogen. Okay, so see how hydrogen is in the 1s block? So my electron configuration is going to be 1s. And now hydrogen's atomic number is 1. So that means it has 1 electron. And I'm going to put that 1 electron in this first s orbital. Okay, now I'm going to jump over to helium. Helium is still in the first row, and it's still in the 1s block. So I'm going to put 1s for helium, but now helium's atomic number is 2, so that means it has 2 electrons. And I know that the s orbital can hold 2 electrons, so I'll put them both there. You don't want to jump and put that second electron in a different orbital because your orbitals with less energy have to fill up first. Okay? So now let's go to lithium. So now I'm jumping down to here. So guys, the electron configuration has to encompass every element before it. So to get to lithium, I have to fill up my 1s rows first. So before I get to lithium, my 1s rows have to be filled up. Now lithium is in my second row on the periodic table, and it's in the 2s block, right? And now as I go across this row here, I just fill up the electrons, 1, 2. So lithium only has 1 more electron in it because its atomic number is 3. So I'm going to put a 1 there. I have a total of 3 electrons. 2 are in the first energy level and 1 is in the second, right? Beryllium is right next to it. So beryllium is 1s2, 2s2. Every time you move to the right, you're adding 1 more electron. When your orbital is filled up, so the s orbitals can only hold 2 electrons, then you have to add a different orbital, okay? And this periodic table tells you what kind of orbital that you're going to add, okay? So for example, when I get to boron, now I jumped over to my 2p block. So let's look at what boron's going to look like. It has to encompass every electron configuration that came before it, 2s2. Now I jumped over in the 2p block, but I'm only in the first spot. As you move over, you add 1 more electron each time, but boron's in the first spot, so there's going to be 1 electron in boron's 2p sublevel. Okay? I want you guys to pause the video, and I want you to try C, N, and F, and O. Actually, you know what? I want you to try, oh my God, now I'm highlighting. I want you to try any also. Okay. Pause the video, try those. I'm going to check your note packet tomorrow. We'll go over them. Okay, now let's look at Na. So Na is right down here. Okay, so Na is in the third row, but like I said before, we need to have every electron configuration that came before it. So I'm going to have 1s2, 2s2, 2p6. The whole second row is filled up. Now I'm jumping down to the third row. I'm in the S block, and sodium is in the first spot. Magnesium is right next to sodium. So I'm going to have everything that came before it, 2s2, 2p6. But now I'm in the third row, the S block, and I'm in the second spot. So there's 2 electrons there. Okay. Aluminum, now that my S block is full, it could only hold 2 electrons. Now I'm jumping over here to aluminum. So I'm still in the third energy level, but now I'm in the P block. I'm going to start filling in the P block electrons. So for aluminum, I have everything that came before it. 2p6, 3s2, and now I'm over on the other side. So I'm in the 3p block, but I'm in the first spot. So there's 1 electron there. Okay. And guys, you can check this as you go. Those little numbers need to add up to 13 because aluminum's atomic number is 13. So if I add up 2 plus 2 plus 6 plus 2 plus 1, I get 13. All right. I'm going to have you guys again try this, and we'll go over this the next time I see you. Okay. Now, valence electrons, these are electrons that are in the outermost energy level. So, for example, let's look at lithium. So lithium has 2 electrons in the first energy level and 1 in the second energy level. So the second energy level is the outermost ring. How many electrons does it have in it? It has 1, right? Let's look at boron. So boron has 2 electrons in the first electron shell, but then there's 3 electrons in the second shell. And since the second shell is the outermost shell, boron has 3. Okay. I want you guys to go ahead and tell me how many valence electrons magnesium has. Okay. All right, guys. So we're gonna look at one more thing today. I think one more thing is good. So you can see that these electron configurations they fill up in order, right? So the only exceptions you have to remember are group 6 and group 11 on the periodic table. So if I scroll back up to this one here, 1, 2, 3, 4, 5, 6. This is group 6, 7, 8, 9, 10, 11, and this is group 11. Okay, 3, 4, 5. Nope, I'm wrong. They go in order, guys. 1, 2, 3, 4, 5, 6. Here's 6, 7, 8, 9, 10, 11. And here's 11. So group 6 and group 11. And on your chemistry reference tables, these groups are numbered. On your periodic table that you're going to have for this unit, they are not numbered for you. So you can go ahead and number all the columns if you want. So basically, if I look at group 6 and 11, group 6 is 1, 2, 3, is the 4th spot over in the D block. And 11 is 5, 6, 7, 8 is in the 9th spot over in the D spot. So as you're filling up the D orbitals, like I would say the electron configuration for this element right here is 4s2, 3d4, right? But there's a rule that d orbitals, so d orbitals can hold a total of 10 electrons. If those orbitals are half filled with 5 or fully filled with 10, they're more stable that way. So instead of 2 electrons in the 4s orbital and then only 4 electrons in the d orbital is going to take that extra electron to get to 5. Okay, so if I wrote out the electron configuration for chromium, right? So argon, it would have everything from argon and before. And then instead of being 4s2 3d4, it would be 4s1 3d5. So this kind of goes against the like Aufbau principle, like we're supposed to be filling it up in order. But to make that d orbital more stable, the 4s can give one away. Okay. Same thing with copper. So copper is in the same row. So it has all the electrons that argon would have. And then as we jump down to the 4th row, I would normally put 4s2 3d9, but since 9 is so close to 10 and the atom would be so much more stable with 10 electrons in the d orbitals, the 4s is going to give one of its electrons to the d orbitals so that I can have a full 10. So any element you get in group 6 or group 11, this is going to be the way that it fills up first. Okay. All right. And one last thing to show you guys, and it'll make this make more sense if you don't know what I'm talking about. There's a way to write a condensed electron figuration. What you do is you look at the noble gas. The noble gas is the last column on the periodic table. You look at the noble gas column and of the element, of the one that came before the element that's given, right? So magnesium is right here. So the noble gas that came before magnesium, this is my noble gas column. My noble gas that came right before magnesium is neon. So I can say, okay, all of these numbers came from neon, and then I jumped down to the 3rd shell and filled up my 3s orbital for magnesium. So instead of writing all of this out, you can just write neon in brackets and then 3s2. So it saves you a lot of time from like copying all of the electron configurations until you get down to the row that your element is in. All right. Gallium is all the way down here, I believe. This is gallium down here, right? So if I look at the noble gas that came before gallium, it's argon. So instead of writing all of this, I would say, okay, all of that came from argon. So let's just write argon in brackets, and then I can start fresh. Okay, in the 4th row, I filled up an s orbital, I filled up my 3d orbital, and I filled up my 4p1 orbital. So that's a nice shortcut. All right, we're going to do lots of practice with this when you guys get back to class. So I'll give you one last question, and I will talk about this with you tomorrow.